I want you to imagine that you are standing in a dark room so large that its walls cannot be seen. There is no ceiling above you, no floor beneath you, only darkness stretching farther than the mind can comfortably hold. And somewhere in that darkness, more than 1 million kilometers from Earth, a telescope the size of a tennis court is staring backward through time. Not metaphorically, literally backward through time. Every photon that reaches the James Webb Space Telescope has been traveling toward us for years, millions of years, sometimes more than 13 billion years. Webb is not simply photographing distant objects, it is receiving ancient messages. It is looking at the universe when the universe itself was young. And for a long time, we thought we knew what those messages should contain. The first galaxies were supposed to be small, chaotic, primitive. They should have needed time to gather gas, build stars, merge with neighbors, grow black holes, manufacture heavy elements, and develop the enormous structures we see around us. Today, that was the picture. Then Webb began to send back its first deep images, and scattered through those images were objects that looked uncomfortably mature. Bright galaxies appeared at epochs where our simulations expected something much more modest. Compact red sources appeared in surprising numbers. Some seemed to hide black holes that had become enormous before their host galaxies had fully grown. One confirmed galaxy now reaches back to roughly 280 million years after the Big Bang. Other systems show organized star clusters and intense star formation at times when the cosmic construction site should, by our older expectations, still have been full of scaffolding. It was like staring at a freshly poured foundation and discovering a cathedral already standing on it. Now, I need to be careful with you from the beginning. Nothing Webb has found proves that the laws of cosmology have failed. In fact, several of the most alarming early mass estimates have already been revised downward as astronomers learned that growing black holes can make these objects look brighter and therefore more massive than their stars alone would suggest. But the mystery did not disappear. It changed shape. The universe still seems to have assembled some things faster than many of our models expected. And in the newest observations, Webb has begun revealing a possibility that is even stranger than a merely oversized young galaxy. Black holes that may have become massive astonishingly early, perhaps in ways that bypass the slow stellar route we teach first in textbooks. We may not be looking at a broken universe. We may be looking at a door in our understanding that was never marked on the map. Before we step through that door together, take a moment to subscribe to this channel if you want to understand what modern astronomy is actually finding without pretending speculation is certainty. Because what Webb is showing us is far more interesting than a manufactured crisis. Now, I want you to forget the phrase distant galaxy for a moment because it hides the most important part of what is happening. I want you to imagine an old family photograph. The photograph is faded around the edges. The people in it are young, although you have only ever known them as old. A house stands behind them before the extension was built, before the trees grew tall, before the road was paved. Nothing in the photograph is moving now, yet it contains information about a world that once existed. Astronomy works in the same way, except the photographs are made of arriving light. When you look at the moon, you see it as it was about a second ago. When you look at the sun, you see it as it was roughly 8 minutes ago. When Webb observes a galaxy whose light has crossed most of the observable universe, it is not seeing that galaxy as it exists today. It is seeing an ancient version of it. Hold on to that image. A cosmic photograph. The farther away we look, the older the photograph becomes. There is another complication. The universe has been expanding while that light travels. Space itself stretches the wavelengths of the light, shifting much of the early universe into the infrared. That is one reason Webb was built to see infrared so exquisitely. Its great segmented mirror and cold instruments are not simply gathering more light than earlier telescopes. They are tuned to receive a part of the ancient universe. That expansion has moved beyond what our eyes can see. For decades, cosmologists built increasingly sophisticated simulations of what those early photographs should look like. The basic framework is remarkably successful. A hot, dense early universe expands, Matter clumps under gravity. Dark matter provides gravitational wells. Gas falls in. Stars ignite. Stars enrich their surroundings with heavier elements. Galaxies merge and grow. Black holes form and feed. Over billions of years, the small becomes large and the simple becomes structured. If you've ever watched a city develop, the intuition is similar. First roads, then foundations, then houses, then neighborhoods, then towers. You do not normally expect the skyscraper before the road. That sequence became one of the quiet assumptions carried into the Webb era, not because scientists believed early galaxies had to be boring, but because building complexity takes time. Gravity works continuously, but not instantly. Stars require gas to cool and collapse. Heavy elements require earlier generations of stars to live and die. Black holes require seeds and a supply of material. Every stage has a time scale, and then the first Webb deep fields arrived. Some galaxies were brighter than anticipated, some appeared surprisingly massive, some existed so early that researchers began asking whether star formation in the young universe had been far more efficient than the standard assumptions in their models. For a brief period, the headlines became extravagant. Cosmology broken, universe impossible, Big Bang in trouble. But science is not a headline. Science is what happens next. Astronomers obtained better spectra. They separated starlight from the light of actively feeding black holes. They revised distances. They improved estimates of stellar mass. Some of the supposed monsters became less monstrous. And this matters because brightness can fool you. I want you to imagine a village at night. We're standing on a hill several kilometers away. Most of the village is dark, but one building contains an industrial furnace with its doors open, and from your distant viewpoint, that one building can dominate the light of the entire village. If you tried to estimate the village population using brightness alone, you might conclude that thousands more people live there than actually did. And accreting black hole can create a similar problem. Material falling toward a black hole does not simply vanish silently before crossing the point of no return. Gas can become compressed and heated to enormous temperatures. It radiates, it can outshine vast populations of stars. If a distant red source contains such a black hole, some of the light we once interpreted as evidence for an enormous stellar population may instead be coming from material spiraling into darkness. That is one reason some of the earliest claims softened. But remember the village, because discovering a furnace where you expected cottages is not the end of the mystery. It is a new mystery. Webb revealed a class of compact, very red objects that astronomers began calling little red dots. The name is almost comically harmless, little red dots. Yet they became one of the strangest populations in the young universe. Many appeared during roughly the first 1.5 billion years of cosmic history. A substantial fraction show evidence that powerful black holes may be involved. And unlike familiar populations in the nearby universe, they do not have obvious modern twins. The coin is rigged, not because nature is cheating, but because the assumptions we used to interpret the light were incomplete. And the early universe was capable of producing a population we had not clearly anticipated. Then something even more provocative emerged. A Webb observed object known as QS01 offered evidence that a supermassive black hole could be enormous relative to its surrounding galaxy very early in cosmic history. More recently, another little red dot, glimpse 17775, has provided unusually strong spectral evidence for a model in which a massive black hole sits inside a dense cocoon of gas. Some researchers describe this possibility with the evocative phrase black hole star. That phrase can be misleading if you imagine a conventional star with a black hole where its core should be. The real idea is more subtle: a rapidly feeding massive black hole wrapped in dense gas whose radiation is reprocessed before escaping. I want you to imagine a lantern inside a thick red curtain. The lantern is extremely bright, but you never see its bare flame. Its light strikes the fabric, is absorbed, scattered, transformed, and then leaks out with a different color if you knew nothing about what was inside. You might look at the glowing curtain and mistake the system for something entirely different. Hold on to that image, a hidden lantern. Now replace the lantern with a black hole feeding on surrounding matter. Replace the curtain with dense gas. Replace the room with a universe less than 2 billion years old. And the question becomes immediate: how did the black hole become so large so quickly? The ordinary story begins with stars. A sufficiently massive star exhausts its nuclear fuel, its core collapses, a stellar mass black hole can remain. That black hole then grows by swallowing gas and merging with other black holes, and the mechanism works. The problem is time. To build the supermassive black holes we observe in the early universe, nature must either begin very early, feed them extremely efficiently, merge them rapidly, start with unusually heavy seeds, or use some pathway we have not yet fully understood. One proposed pathway is direct collapse. Instead of building a large black hole from the corpse of an ordinary star and then waiting through repeated episodes of growth, a massive cloud of primordial gas might collapse under special conditions into a much heavier initial seed. I want you to imagine two ways of building a ship. And in the first method, you begin with a canoe, you bolt on more wood, you strengthen the frame, you attach a motor, you rebuild the hull. You repeat this process over and over until, after many stages, you finally have something resembling an ocean vessel. In the second method, you begin in a shipyard with enough material to assemble a large hull from the start. The second route does not violate the laws of shipbuilding. It changes the initial condition. And that may be the lesson Webb is forcing us to consider about early black holes. The cosmos may have had shipyards where we assumed there were only canoes. Here is the hard truth. Whenever an observation appears impossible, there are at least three broad possibilities. Our measurement is wrong, our interpretation is wrong, or our model is incomplete. Science survives because it does not get to choose among those possibilities based on emotional preference. The data must decide. That is why Webb spectroscopy matters so much. An image can seduce you. A spectrum interrogates the light. By spreading light into its component wavelengths, astronomers can identify chemical fingerprints, estimate redshifts, probe gas motion, distinguish starlight from active black hole emission, and infer physical conditions that a beautiful photograph alone cannot reveal. A spectrum is not a portrait, it is testimony. And the testimony is telling us that the first billion years were crowded with activity. Galaxies formed stars rapidly. Some built compact stellar systems earlier than expected. Some hosted growing black holes. Some may have converted gas into stars more efficiently than the recipes used in older simulations assumed. And some objects appear to occupy categories that were not obvious before Webb. This is where human intuition entirely breaks down, because our brains are not built to understand cosmic growth from first principles. Look around the room you are sitting in right now. Nearly every object you see was assembled under conditions of extraordinary stability. The temperature changes slowly. Gravity is essentially constant. The floor remains where it was. The atoms in your desk, your phone, your walls have already been processed through generations of cosmic history. The early universe was not like this room. It was denser, hotter, more rapidly changing. Gas was abundant. Radiation fields were different. Chemical composition was different. The background universe itself was different. Using the local universe as the default template for the early universe may be like using the rules of a quiet pond to predict a waterfall. I want you to imagine that pond. The surface is smooth. You drop a leaf onto it and watch the leaf drift gently. From those observations, you develop an elegant theory of water. Water is calm. Water supports leaves. Water moves slowly under small forces. And then someone takes you to the edge of a canyon and shows you a waterfall. Nothing about the waterfall violates the physics of water, but your theory of typical behavior collapses because your sample was too narrow. Hold on to that image, and the early universe may be our waterfall. One of the remaining puzzles is simply abundance. Even after removing some objects whose masses were exaggerated by black hole light, Webb observations still indicate more massive early galaxies than some models predicted. Not impossibly massive galaxies, but enough of them to make astronomers ask whether the efficiency of converting gas into stars was higher in the young universe. That may sound like a minor adjustment. It is not. Star formation is one of the central engines of cosmic history. Change its efficiency, and you change when galaxies brighten, how quickly heavy elements accumulate, how rapidly feedback from supernovae reshapes gas, and how the first large structures emerge. Imagine that every model of city growth assumed that only 5% of available construction material could be used each year. Then you discover an early city that seems to have used 15%. The laws of architecture remain intact, but the timeline changes dramatically. The coin is rigged again, not because nature cheated, but because one of the probabilities we fed into our expectations may have been wrong. And this brings us directly to the most unsettling word in the title, structure. What does it mean for a structure to exist too early? It does not mean a physical law explicitly forbids it. And usually it means that given the standard assumptions in our models, assembling that much organized matter by that time should be rare. Rare is not impossible, but when rare things appear repeatedly, the model must account for the pattern. This distinction is essential. If I roll a die once and get six, nothing interesting has happened. If I roll it 10 times and get six every time, the laws of probability have not failed. But you would be foolish not to inspect the die. JWST is making us inspect the die. Some of the most distant galaxies are brighter than expected. Some are chemically enriched surprisingly early. Some host black holes that seem disproportionately developed. Some show star clusters at epochs where we are still learning how quickly clustered star formation could proceed. Any one observation might be absorbed by uncertainty. The population is what matters. And now I want to take you somewhere deeper. Suppose the early universe really was extraordinarily efficient at building structure. Why? One possibility is simply density. In a younger universe, matter was packed more closely. Gas flowing into early dark matter halos may have arrived rapidly under the right conditions. Feedback that would normally expel gas from small galaxies might have been less effective at stopping star formation than older models assumed. Another possibility is that black holes themselves altered the apparent story. If some black holes form from heavy seeds or by direct collapse, then they could become powerful sources of radiation very early and contaminate our estimates of stellar mass. Another possibility involves the stellar population. The first generations of stars formed from gas with extremely few heavy elements. Their mass distribution may have differed from the stars forming around us today. If early stars were systematically more massive, their light output per unit stellar mass could be different, again, affecting what we infer from distant observations. And there are more speculative possibilities. Perhaps some ingredient in our treatment of dark matter feedback or early structure formation needs modification. Perhaps not a revolution, but a correction, a coefficient, a threshold, a process that was always permitted by the theory, but underestimated in practice. This is where the difference between physics and storytelling becomes painfully important. A storyteller wants one answer. Nature often gives us a degeneracy. Several different mechanisms can produce similar light. The astronomer's job is to break that degeneracy. That is why Webb is only one part of the emerging picture. X-ray observatories, ground-based telescopes, gravitational lensing surveys, and future instruments can test whether these red compact systems really hide rapidly. Accreting black holes, how massive those black holes are, how large their host galaxies are, and how common the phenomenon becomes at different cosmic times. The hidden lantern must be examined from more than one direction. And now something massive and unknown is swimming in that dark ocean, not a monster, an unanswered formation pathway. Think about the sheer weight of this. For most of human history, the sky was a ceiling. Then the telescope made it a landscape. Spectroscopy made it chemistry. Relativity made it geometry. Quantum theory made matter itself probabilistic. And now instruments like Webb are turning the earliest universe into an observable laboratory. We are no longer asking only what the universe is made of. We are watching how it learned to make itself complicated. That sentence deserves to be taken seriously. How did simplicity become structure? Hydrogen and helium became stars. Stars became chemical factories. Galaxies became ecosystems of gas, dust, stars, magnetic fields, black holes, radiation, and dark matter. Eventually, in at least one galaxy, chemistry became biology. Biology became nervous systems, and nervous systems became capable of building a telescope that could look backward toward its own origin. You are part of the structure. Webb is trying to explain the iron in your blood came from earlier generations of stars. The carbon in your cells was manufactured by stellar nuclear reactions. The oxygen you are breathing while listening to this was created inside stars that lived and died long before the sun formed. The universe did not begin with people, it began with conditions, and somehow those conditions became you. This is the existential power of the Webb mystery. If the first galaxies assembled faster than expected, then the pathway from a nearly uniform young cosmos to a richly structured universe may have been more vigorous, more efficient, and more surprising than our simplified stories suggested. We did not misunderstand the destination. We may have underestimated the speed of the journey. Now return to the old photograph. At first, we believed the photograph showed a primitive village. Then Webb sharpened the image and we saw lights that looked like towers. We panicked and wondered whether the entire history of the city was wrong. Then spectroscopy revealed that some of the towers were actually furnaces, brilliant enough to distort our estimates. But when the glare was removed, the village was still more developed than expected, and behind some of the brightest curtains, there may be engines we did not know could become powerful so early. The metaphors begin to converge. The village contains a furnace, the lantern is hidden behind a curtain, and the pond becomes a waterfall. The dye keeps landing on six often enough that we have to inspect it. This is how scientific revolutions usually begin, not with one dramatic declaration, but with a growing collection of details that become increasingly difficult to ignore. Newton did not become useless when Einstein arrived. Newtonian mechanics remains extraordinarily accurate in the regime where it applies. Einstein did not become useless when quantum theory revealed a deeper description of matter. General relativity still predicts planetary motion, gravitational lensing, and black holes with astonishing precision. A successful theory is rarely thrown into the fire. It is placed inside a larger theory. That is why phrases like JWST broke cosmology miss the beauty of what may actually be happening. Cosmology is being tested, and that is what we built Webb to do. A theory that cannot be exposed to observations is not physics. The purpose of a telescope is not to decorate the theory with photographs, it is to threaten the theory with reality. Sometimes the theory survives, sometimes the assumptions surrounding it change. Sometimes a parameter we thought was universal turns out to depend on environment, and sometimes, very rarely, a crack widens into a door. We do not yet know which kind of moment this is. My own suspicion is that the most dramatic headlines will turn out to be wrong in the simplest sense. We are probably not watching the collapse of the Big Bang model. We are probably not seeing galaxies that literally violate known physics. But I also suspect the comfortable pre Webb story of early cosmic growth will not survive untouched. And there are too many interesting clues now, too many early galaxies, too much rapid star formation, too many strange compact red sources, too many massive black holes appearing before our intuition says they should be comfortable there. That is not failure, that is discovery. The greatest instruments in science have always done this to us. They enlarge the observable world and, in the same motion, expose the narrowness of our expectations. Galileo's telescope turned points of light into worlds. Hubble's observations helped turn the universe from static scenery into an expanding history. Radio telescopes revealed pulsars and quasars. X ray astronomy exposed a violent, high energy cosmos, invisible to human eyes. Webb is revealing the infrared childhood of structure, and childhoods are always messier than family stories make them sound. Journeys like this, deep into the edge of human knowledge, require time, careful reading, and a willingness to separate what the evidence says from what we wish it said. If you value that kind of exploration, the super thanks option below this video is one way to support the work and help us keep following these discoveries as the evidence changes. But the most important thing you can bring is curiosity, disciplined by patience, because the next Webb spectrum may erase one of today's mysteries or deepen it. The next object may reveal that the black hole star picture applies only to a narrow class of little red dots, or it may show that early black holes commonly formed through channels we once treated as exotic. Better, measurements may bring galaxy counts closer to simulations, or they may force simulations to make stars faster. That uncertainty is not a weakness in the story, it is the story. We began with a telescope in darkness, collecting ancient photons. We followed those photons into an old photograph of the young universe, and we found a village that looked too bright, and we discovered furnaces inside it. We pulled back a red curtain and found the possibility of hidden black hole engines. We stood beside the calm pond of our local assumptions and realized the young universe may have been a waterfall. And we inspected the die because the same strange outcomes kept appearing. And now we are back at the door. Have we opened a passage to new fundamental physics? Perhaps, but the evidence does not require that conclusion yet. What we can say is more precise, and in my view, more profound. Webb has shown us that the universe became organized, luminous, and structurally ambitious with astonishing speed. Some of the objects we once thought were impossibly massive were exaggerated by hidden black holes, yet those black holes themselves may now be the deeper mystery. The structure that should not exist may not be one forbidden galaxy. It may be the architecture of rapid growth itself. A young cosmos building stars, clusters, galaxies, and enormous black holes before our old intuitions were ready for them. And the door is open. And the question on the other side is no longer whether the universe broke our rules. It is whether our rules ever captured how creative the universe could be. And if they did not, what will the next ancient photon force you and me to rethink?